indeed, you can continue this game. You can think of 3 water types. So you have 3 overlaying layers, 3 layers. Okay, you have a red layer, the lightest at the surface. Then you have a green layer, it's an intermediate layer, and you have a blue layer, a deep layer. The density is stably stratified, which is shown here. The density vertical profile on the top right. Have a look here. Light water density increases with the second layer and it increases even more as you go down. But you have one example where the temperature and salinity are both the lowest in the green layer. Okay, so you have the lowest salinity in this green layer, but it's compensated, or it's offset by a lower temperature in terms of the salinity. Okay, and if you now show these 3 original water types in a TS diagram, you get these 3 dots: a red dot for the top layer, a green dot for the middle layer, and a blue dot for the bottom layer. Also shown are the isopycnals, the density contours. On the left, you have the light water, and on the right, you have the dense water. See, as you move from the red to the green to the blue, the density increases. So now how mixing happens in this example is mixing happens at the interface. Okay, you can see the mixing, what mixing does. Okay, it mixes away these sharp transition zones and you get smoother connections. Okay, these are the dotted curves in these 3 properties here: temperature, salinity, and density. And you can see you also get 2 mixing lines between red and green and between green and blue. And if you get strong mixing, the final mixing product, the curve that you observe, might actually no longer be connected to the green. Okay, so this part of the signal, you still see a nose structure in your TS diagram, and you can see that where the line comes close to the green, you get actually a high contribution, mixing contribution of the green water map. Okay, so now this is exactly what you need in order to understand these nose structures in TS diagram. And I want to show you one example. Or before we do that, just the equations. You have 3 layers. How do the mixing equations look like? Okay, mixing equations look like this. You have 3 fractions called V1, V2, and V3. And the sum of these fractions has to be 1. Okay, for example, you have 20% of one water type, then you have 60% of the other one. Okay, then you have to have 30% of the third. And then the mixing product is you just put it all in one bowl, and then you have 1 fraction of T1 plus the second fraction of T2 and the third fraction of T3. You put it all together and you should get the observed temperature, the mixture. And you have another equation for S, for salinity. Okay, and if you have additional information, just like dissolved oxygen or other, chemical elements, it becomes a little bit more complex because you also have decay, okay, and chemical reactions or so. It becomes more complex. It's easiest with temperature and salinity because there are conservative properties. No decay, no internal source. Again, you end up with 3 equations with 3 unknowns, or you get 1 solution. Okay, you get 1 solution in terms of how much the fractions are the unknowns. Okay, V1, V2, and V3. Okay, let's have a look at an example.